You know, some of the biggest ideas in science, the forces that shape our entire world, are completely invisible. So how do we start to understand them? Well, today we're going to see how the most complex principles are often best learned not from a book, but by building, touching, and yeah, even playing.
I mean, that's the big question, isn't it? For any teacher, for any student, it's a huge hurdle. How do you make something like gravity, this force you can't see, actually feel real? How do you create that spark, that genuine aha moment where it all just clicks? And the answer, it turns out, is beautifully simple. We put the lesson right into a student's hands. Because when we use physical models, these huge abstract ideas suddenly become something we can feel, something that makes sense, and something we'll never forget.
So, here's our game plan for today. We're going to start by uncovering the secrets of strong structures. Then, we'll dive into the incredible power of the lever. After that, we'll see how to make invisible forces visible. And finally, we'll wrap it all up by talking about what this all means, the real lesson in our hands.
Okay, first up, let's talk about one of the most amazing feats of engineering, the bridge. How on earth can a simple little model teach us the secrets that let these massive structures hold up literally tons of weight every single day?
The secret? You know, it all comes down to a really simple shape, the triangle. A truss bridge is basically just a whole bunch of triangles linked together. And why is that? Well, because triangles are incredibly good at handling force. When you push or pull on them, they don't fold or buckle. They spread that force out. For a student building one, that's the first aha moment. Strength isn't just about heavy materials, it's about smart shapes.
And this is how a teacher can take something huge and complex and make it totally understandable. They can just point to the model. See this? That's the deck. These are the towers. And those diagonal pieces? Those are the rock stars. They form the triangles we were just talking about, managing all the pushing and pulling. All of a sudden, a student isn't just looking at a bridge, they're actually seeing the physics that holds it all together.
All right, so from holding things up, let's move on to lifting things up. We're going to look at a simple machine that is so powerful it literally changed the course of human history, the lever. It's the key to everything from a seesaw on the playground to those giant cranes building skyscrapers, and with a hands-on model, its power is something you can feel immediately.
You know, no matter how complicated a machine looks, if it's a lever, it boils down to just these three parts. You've got the load you need to move, the fulcrum or pivot point, and the effort you put in. Once a student understands how those three things relate, they've just unlocked the core idea of mechanical advantage, how a tiny push can create a massive amount of lift.
And this is where play turns directly into a physics experiment. We're actually rediscovering an ancient law of the universe right here. When a student slides that fulcrum around on a model and feels how much easier or harder it is to lift the load, well, they're performing the exact same experiment that Archimedes figured out more than 2,000 years ago. That's powerful stuff.
And this is how a teacher can show how the same idea scales up. You can start with a simple marionette, right? The strings and joints are all just levers making the puppet dance. Then, you move to a simple lifting model to show that raw power, that mechanical advantage. And finally, you scale it all the way up to a tower crane, where that same lever principle, plus a clever counterweight, lets us build cities. Each model builds on the last, and the lesson really sticks.
Okay, but what about those forces we can't see at all? Let's get into how these models can take these really abstract physics concepts, things like gravity, friction, and lift, and turn them into something a student can actually see, feel, and control.
Mass versus weight. Oh man, this one trips up so many people, adults included. But with a simple balance scale, a teacher can nail this concept. The scale balances because it's comparing mass, the amount of stuff in an object, and that doesn't change no matter where you are. It gives a perfect visual for separating mass from weight, which is really just gravity's pull. When that scale hits equilibrium, it's like a physical picture of an abstract idea. How do you teach friction? Sure, you could write a bunch of equations on a whiteboard, or you could just let a student roll a marble down a track. They can literally see it slow down. They can swap out the track for a smooth one, then a rough one, and feel the difference. The model turns friction from just a word in a book into a direct sensory experience. It's the force that stopped their marble.
And this is where things get really magical. We unlock the secret of flight. A model of a bat's wing shows you everything you need to know. The top is curved and the bottom is flat. So as air flows over it, it has to travel farther and faster over that curved top. And here's the rule. Faster air means lower pressure. That simple pressure difference creates an upward push, and we call that lift. When a student flaps this model, they can actually feel that tiny bit of resistance, the start of that lift. They're connecting a simple action to one of the most fundamental principles of flight.
So, we've built bridges. We've lifted heavy things. We've even felt the forces of flight. What's the big picture lesson here? What do all these incredible models teach us about the act of learning itself? When you look at it, across all of these seemingly simple models, students are getting hands-on with some seriously deep STEM concepts. They're learning about engineering, physics, and even math, not as boring, separate subjects, but as connected ideas that explain how the world around them actually works. These aren't just toys. They are amazingly efficient teaching tools.
And really, that's the ultimate point. The real power here is that these models build a bridge between the words in a textbook and an actual physical experience. They're designed to create those fantastic aha moments, that instant a tough concept finally clicks into place, not because a student read about it, but because they built it, they tested it, they saw it with their own 2 eyes.
So it leaves us with this really powerful question to think about. What if every single complex lesson, whether it's in economics or chemistry or biology, could be boiled down into something we could actually hold and touch and understand on a deep physical level? What would that change about the way we all learn?